So I was asked to give a little bit of an overview of the usage of machine learning in physics. And I took the chance to discuss a little bit what was done at the time of the Higgs discovery and the kind of new perspectives opening up now. And I'm gonna just give you a few examples because the field is very active and it's growing and people are coming out with very good ideas. And so this is just too much to be covered in 1 hour. So since we are here celebrating the Higgs discovery, I will also like to put it in the context, the machine learning development and the endorsement of machine learning techniques in the LHC physics in the context of that discovery. You know that the Higgs discovery was basically the minimal deliverable and the basic and the baseline of the Higgs, the DCMS and advanced physics programs. And that's such that the detector have been really designed in order to do so. On the other hand, once you have, so clearly without the detector, you would not have it discovered. But the next question after, wait a sec. After you design your detectors in the best way you can, the next question is how you can maximally take advantage of them. Clearly, we did manage to discover the Higgs, but in these two pictures that you see here, the summary of this successful story, there is a little bit of machine learning hidden in the details. And the details comes with the typical usage of machine learning that we do in energy physics, just to do effectively with two main tasks that were explored so far, classifications and regression tasks. So kinds of classifications are identifying real particles like the photons from the Higgs boson from fakes that could originate from spurious effect in the detectors, from deposit of energy coming in jets that will look like photons and so on and so forth. And clearly there is a higher level of that, which is once you have your analysis defined and you separate the signal from the value. Regressions are the typical example of regression is how do you measure the energy of a particle that you see. Now, we do measure energies without need of machine learning, but as a matter of fact, the response of our detector depends on a lot of things, like the position of the cluster, the conditions in which things were taken, what's happening nearby the particle you're trying to reconstructing. And so this becomes very easily a multidimensional problem, and machine learning is a way to deal with multidimensional problems while exploiting correlations at best. So far, these tasks in the history of the LHC I'm talking about, this task has mainly been addressed with BDTs. And now we're gradually switching to deep learning, which is what I'm gonna talk in the mostly today in terms of future perspectives. And this is actually very interesting because deep learning comes with new kind of possibilities that open up new opportunities. And we're gonna see a little bit of that. But going back to the discovery of the Higgs, clearly this is just the last episode of a long tradition of usage of machine learning in energy physics that dates back to the LAP and then Tevatron with the usage of neural networks. The B factories, particularly Babar, took this as an inheritance from LAP and then pushed it to the next level when Mini Boone introduced BDTs in energy physics. Babar was a very early endorser of this, and actually Emanuele, who is connected, in my memory at least, was one of the first to start working with BDTs at the time of his PhD thesis in Babar. These BDTs then were ported to the LHC, to CERN, when the B factory, when Babar faded away, and they were very useful for the Higgs discovery. The plots on the right, they were made for a recent review, it's a couple of years old by now. I think it was on Nature, of the usage of machine learning in energy physics. And these two plots tell the same story. On the x-axis, you have the Higgs boson mass, which was clearly not known at the time. And the y-axis tells you the same thing in two different ways. On the top, you have the number of sigmas, and in the bottom, you have the minimum amount of data that you need to cross the 5 sigma line. And so what you see, So the top is number sigma in some unit of luminosity. I think this was the luminosity of the 2011 pre-discovery results. And the thing in the bottom, it's actually maybe the most striking, is how much data would you need to cross the 5 sigma discovery line in units of the data that we had in December 2011, when we started to see the footprint of the Higgs boson. And the yellow line is a rule-based selection of the photons that basically put cuts on the things that shape of the cluster of the energy to separate the real photons from the fake photons, and then you would use that photons in the Higgs analysis. The one in the bottom does the same thing with ability. And you see that basically you go from a factor of 3.5 to factor of 5. So this would have cost you in terms of luminosity if you didn't use machine learning techniques. And this is even an underestimate of the importance of the abilities, because both the yellow and the blue line, in any case, use an energy regression based on machine learning. So even the orange line is not really machine learning free, but let's say it is the first approximation. So this is telling you that machine learning had the strength to maximize the importance, to maximize the handles given by our detectors to us in order to discover the Higgs and anticipated the discovery. And indeed, if you look back at the pre-LHC papers, particularly to the TDRs of the Atlas and CMS, nobody would have anticipated that running for so short at an energy which was half the energy that was initially foreseen, we would have discovered the Higgs so early. Most likely we would have discovered it in 2016 or so. So this is to tell that certainly machine learning was functional to discover. Now, from these premises, I'm gonna go a little bit too much into details, because I don't know if you are all experts of this or not. So assume that there are people who might not be super familiar with machine learning, but might have some understanding of what it does. Effectively, machine learning is a name by which we refer to a huge set of techniques, of algorithmic techniques, in which the algorithms are not programmed to solve a task, but instead they learn how to solve the task by looking at examples. The typical construction is that of a supervised learning. The classifications and regressions I referred to so far are examples of supervised learning, where one has a training data set, and for this training data set, true answers are provided. For instance, in our case, this could be like for Monte Carlo simulation. And one defines a machine learning algorithm, which effectively is a huge function with a lot of free parameters, and looks for the best configuration of these parameters such that the prediction provided by the algorithm matches the true answer. And the matching is quantified through a loss function, which defines the problem. Could be a classification problem, and so your loss function is going to check how many times you associate the right object to the right class, a given object to the right class. It could be a regression, so in that case, it could be, the loss function could be a mean square error between, I don't know, the predicted energy and the true energy of the particle, and so on and so forth. So what you do is that you start from a multidimensional training data, and you typically go for a lower dimension output that could just be one number or one class. There are many flavors of machine learning. So we already mentioned the boosted decision trees, which were one of the alternatives to neural networks that emerged. But before the 90s, let's say, neural networks dominated the field, and particularly shallow neural networks, like the one which is represented there, which has only one hidden layer. So you have one input, one output, and in the middle there was one layer that was connecting the input to the output. And we call them shallow now to differentiate them from the deep neural networks, which we're going to discuss later. But also support vector machines, which didn't have a lot of usage in high energy physics, but they were considered at some point the best options on the market. Now, machine learning is about two steps. As we said, there is a step of learning where the algorithms learns by examples on how to tune its parameters to accomplish the task at best. And then there is the inference, which is when you then take this algorithm and you use it, which sounds like a trivial thing to do, but depending on where you're doing it, could actually come with complications. And we're going to talk about that at the very end when I'm going to go towards the trigger. There are several kinds of learning. I discussed that so far we have mainly used supervised learning, which is I give you the data, I give you the right answer, and you try to learn the function connects the two. But there could be tasks in which answers are not given, like a clustering problem, which is an example of an unsupervised learning. We're going to talk about this later. There are, between these two, there are a lot of intermediate shades, like weakly supervised, semi-supervised. I'm not going to talk about that, but it's just to tell you that the spectrum is a little bit more bigger. Then there are other things that we typically don't do, like reinforcement learning, which is more the domain of AI development, where you are really trying to train an algorithm to take decisions. Now, as we said, for us so far it was mainly given classification and regressions, and these are problems which are very popular even outside our field, like image recognition is an example of classification, but in particle physics, the equivalent of that is identify a particle. The difference is in the way the data is represented. And also regressions in general, we talk about regression where, unlike the classification, the outcome is a continuum quantity, f of x, a function of some input x. And the example of the energy of the particle is just one of the many possible. So in the case of the discovery, the machine learning was mainly injected on the gamma channel, which was less experimentally clean, because the 4-lepton final state, the golden channel, was so clean that people didn't use much machine learning there. Then at some point, of course, there was even the possibility there to use a full likelihood. And of course, if you have your problem and you know the full likelihood of your problem, you don't even need machine learning, because you have an analytical function to model the correlation between quantities. Instead, in the diphoton final state, this was not true. And the performance there, for instance, you have your reconstruction of photons depends on where you are on the detector. It can depend on what's happening around the detector. It's really a multidimensional problem. It's not just you record the energy of the object and that's your energy. That's the energy you measured, but then you try to go from the energy that you measured to something which is as close as possible to the true energy. And this is where you use machine learning. So effectively what you're trying to do, you're trying to take an n-dimensional problem, you're trying to move it down to a one-dimensional problem, exploiting all the possible correlations. But this is a constant of the reason why you would use machine learning. It doesn't make sense to use machine learning if you have a one-dimensional problem. It doesn't make a lot of sense. And it doesn't make a lot of sense to do it if you have an analytical, if you already know analytically how to go from your X to your answer. You just use your analytical knowledge. In any case, this, on the other hand, I would like to stress a few things. This really dates back to the 90s. So this idea of taking an n-dimensional complex program and try to use machine learning to bring it down to one dimension, something was already done in the 90s at lab in the context of B tags, in the context of improving the determination of B's. And this again had to do with the Higgs, because X2BB was one of the search channels on that. And also the problem of reducing, the problem was the same. So you want to reduce the backgrounds and the dimensionality of your problem into one-dimensional object. But I would like to stress also that at the same time, people were already thinking beyond classification and regression. People were thinking in terms of using neural networks to solve the very, very basic problems of pattern recognition that we have in collider physics, and particularly on tracking. These are things that today are considered very natural fields where you will apply neural networks, but at the time proposing something like this, it was a little bit of a revolutionary step to do. And the main limitations, the main reason why this didn't happen so far has to do with it was really not possible to train models which were complex enough to take all the complexity of that problem with the technology that was available at the time. For that to happen, we had to wait for deep learning. So deep learning is just a very, very vague name that tries to cope with the fact that there are many, many kinds of neural networks. I mean, this is looking an image on the right that shows you that there are several kinds of neural networks you can come out with, simply because neural networks are made of nodes connected by edges, and there are a lot of ways you can arrange nodes and edges. And depending on how you arrange things, you accomplish different tasks. We're gonna see a few of them in the next. But the point is that what does this have to do? Where does the deep comes in the game? Deep basically means that there is more than one hidden layer. So, and this is why people started to talk about deep network as opposed to shallow networks that we saw before, just because these networks have more than one layer. Having more than one hidden layers, the complexity of this network grows very, very quickly with the depth, much quicker than with just making the network wider. And so it was possible with relatively less nodes to approximate more and more complex functions. The main limitation before, it's not that nobody ever thought about adding hidden layers, is that people didn't know how to train them. And this changed when it was realized that GPUs could be used to do this. And in particular, when the backpropagation algorithm that looks for the best configuration of the weight, so the minimization of the loss function, was ported into the GPU's hardware. And this happens basically at the same time when we were discovering the Higgs boson, or we just realized a little bit later because we were otherwise busy at the time. So once this happened, the technological power increased, and then people started to also get a little bit more creative with new architectures and new ways to actually exploit this new technology at hand. And what happens is, what we know is that now artificial intelligence research entered our daily life through neural networks, deep neural networks accomplishing very complex tasks like driving, like understanding words and the meaning of words and replying to that in a sort of conversation, clustering algorithms like your favorite movie platform suggesting you what you might like to watch next, and down to playing very, very, very complicated strategy games like Go, beyond human capability. In the next, I'm trying to concentrate mainly on feed-forward neural networks, which are those that we typically use, but they are not the only one that exist. A feed-forward neural network means that the input of the network comes on one hand, and then it goes through a series of layers that are connected through the previous and the next layer, but there are not like loop connections. Then you have, after you go through all these layers in the right order, you get out on the opposite end. If you just look at the deep neural network of the basic kind, the one depicted there, which is usually called dense neural networks or multi-layer perceptron, what does it do? It takes your inputs and multiplies them by weights, which depend on two indices, the index of the input and the index of the node. So you can represent mathematically each layer as basically a table of numbers. And then you sum across your inputs, you add one bias, and then you apply the activation function. And this is where the magic happens, because the activation function is the thing that brings in the nonlinearity. So far, up to here, the only thing that you have done is to rotate and translate your inputs. At this stage, you introduce nonlinearity through the nonlinear activation function. There are a few examples there. And this is what makes the neural networks universal approximators, because at this stage, they have the capability of approximating nonlinear patterns. And a neural network eventually is a function of a function of a function of a function, something like that. And you can look at it as a function that goes from some n-dimensional input to some k-dimensional output space. And there is a theorem that says that under certain smooth conditions, you can basically approximate any function from Rn to Rk, which is good for what you want. Now, why using deep learning? In general, the answer is different if you think at the outside world and if you think at us. I mean, people in the outside world use deep learning because it's extremely effective in finding answers to the questions that people have. Like computing vision, identification of objects from images, it's something that is very, very complicated problem without deep learning. You can have accuracies if you are extremely good of 20, 30% maybe. Well, in this case, you immediately jump to something like 99% accuracy. This is not why we do this. Why? Because we already have an established baseline. So we do have understanding of the physics of the problems we have at hand. We have the computational power to implement this understanding into algorithms that give us, from the whatever data we detect, answers to the question that we might have, which is which kind of particle was produced, which energy did it have, where was it going, and so on and so forth. The problem that we have is that with the LHC in particular, but in general with the energy physics facilities delivering more and more and more data, it becomes more and more complicated to actually get these answers in time without spending any huge amount of computational power. If you had infinite computational power, most likely you would use, I'm not saying no deep learning at all, but much less of it. You would run your tracking for a luminosity LHC with the standard tracking that we already have at place. It would just take much more computing power, but you have infinite computing power, you don't care. We don't have infinite computing power, so we need to be quicker and we need to use limited resources. And so the neural network comes in as a very quick and cheap, relatively cheap way to go from the input data to the answers that a rule-based algorithm can provide. In some sense, this is why most of the things that we do are supervised, is because we are a baseline and we are trying to approximate that baseline. And now, with deep learning, this goes well beyond regressions and classifications, because deep learning has the capability of scaling very quickly, very well with the number of inputs, so that you can feed deep learning algorithms directly with the raw data. And at this point, you can start to do more fancy things. People have proposed using deep learning as an event generator to speed up GEANT and eventually to replace it, maybe. To do anomaly detection, I'm going to talk a little bit about that. To search basically for new physics as an outlier of standard events. To control systematic effects using something which is called adversarial training, and I'm not going to discuss for lack of time. Even to do jet grooming, so taking the jets and taking out the pileup and the soft stuff in order to look at the jet substructure, using reinforcement learning, which is basically AI kind of application. So this is all possible because it is now possible to feed the network directly with raw data. It doesn't mean that your machines operate by themselves, but as a matter of fact, you don't have anymore to take your data, translate your data into a limited set of quantities that catch the physics of the problem that you have at hand, and then solve them with ability. You can go straight from the data to the solution. Now, why is this useful? Because as I said, we have clearly a big data problem. So as you might know, the LHC produces something like 40 million collisions per second. We can only solve thousands of them. So we have a big deal of what we do is actually to process this data in real time and go from 40 million events to 1,000 interesting events based on some definition of interesting that we have, which is related to the physics we want to do. So we need to act very quickly in that small time window between one event and the other, which thanks to buffering and things reduces to something like 100 milliseconds. But at the same time, we have to do it keeping in mind that our data are very special. They're not images, they're not text, they're not the bread and butter deep learning kind of things. And so we have to develop our own solutions. And this is particularly due to the fact that our detectors are irregular objects where sensors are not arranged in regular patterns. And so, and also the fact that most of the detector during collision is empty. So we need to add on sparse, irregular geometry data in a very small amount of time. And so this makes our problems a little bit special, and it's not just sufficient to go and take whatever Google and Facebook are developing. You need to act on your own. So I'll give you a little bit of a few examples of what we do. So as we said, the main problem is the sparsity and irregularity, geometrical irregularity of our data. It's not a unique feature of our field in the sense that there are other fields in science which have the same characteristics. Imagine, I don't know, chemistry or astrophysics. You can look at this data, even if when they are images, you can look at them as a sparse data sets. You can represent them as a list of items that are listed according to their coordinates and whatever other characteristic they have. Look at the image that you have on the bottom left of the slide. You have an image of black and white squares. You can represent it with the image itself, or you can just represent the field squares, the black ones, with their coordinates. And if it's not a black and white image, but it has some kind of grayscale, you can add the third coordinate, which is the grayscale. And so you see that you are turning whatever sparse image into a list of numbers, and this list of numbers, then you can try to process it. And a way to process it is through graphs. What are graphs? Effectively, they are like a neural network where you try to connect all the dots in all the possible ways. And this is effectively what a graph net does. You start working from your dots, you connect the dots that you think are relevant. And if you don't know which are the relevant ones, you connect all of them. And then you ask your network to learn which are the relevant connections. And you can then from there recycle a lot of the things that are done on images and text, but in a different context, which is a context of graph neural networks. So when you build the graphs, effectively what you do, you start from your vertices, which in our case would be, for instance, the hits of a tracker device or the energy deposits into a calorimetric detector. And you connect them with these connections. And then what you do is that you are trying to learn the feature of one of these objects, of these vertices, from the nearby vertices it's connected to. And this is done with something which is called message passing. I'm not gonna go through all of this because I'm running a little bit late. But this is basically a kind of neural network that was developed and was found to be very, very adapted to the data that we have. So effectively, you might be familiar with convolutional neural networks, which are those that are used to process images. This is a generalization of that. It's called EdgeConv, but taking as input an irregular graph as opposed to a regular table of pixels. And it has very similar performance, except that it doesn't struggle with sparsity. You don't have to carry over with you all the pixels which are zero. That would take a lot of your memory. And so they are more economical from a computational point of view. And now, in our case, what we notice is that still they're big. And so we came out with even more economical versions of them, which adapt very well to for instance, to the physics of the next calorimeter of CMS, the GCAL. And these networks, again, I'm not gonna go too much into the detail because otherwise I will not finish in time. But they are basically designed in such a way that on one hand, they are effective, and on the other hand, they are computationally light. There are two architectures that we come out to. They differ a little bit in the details. But the nice thing is that you can try to solve problems of this kind. You have a calorimeter, you have particles that go into that. The particles will release energy in the different senses that you have, but you don't know which energy comes from which particle. And you would like to disentangle that this is basically what we do when we do clusters. We cluster hits into particles. And on the left, the red and blue gives you the case of two overlapping particles, but we did it with as many as hundreds of particles. You have the two overlapping particles, and the color tells you which particle they come from. The thing on the left is the truth, is the truth that you know because you simulated this event, so you can actually know what happened. And then the sides of the dots is how much energy was deposited. On the right, you see what the network reconstructs, and you see that it goes very, very close to the actual reconstruction, to the actual configuration. And then the nice thing is that if you now do this with the EdgeConv networks or with the architecture that we design, you typically have the same kind of performance in terms of reconstructing the right energy, so the response, and the resolution, so the uncertainty that you associate to this reconstruction. You see that you are very close to, so the edge conf, the architecture that we imported from computer scientists is what is called their DGCNN, and it's a blue one. And the others are those that we come out with. And you see that you can actually match the performance of that one. But then if you look on the bottom, where you see the time and the memory that it consumes, you are way, way better than that. This is important, for instance, if you're gonna try to imagine that you will run this kind of applications in real time in order to handle those data that are coming in your detector. You would like to keep the time small, and you would like to use as little memory as you can. And this is basically the kind of direction we are taking. So you see that you can start with some off-the-shelf architecture that computer scientists are developed, but then you need to adapt it to your needs. I'm going to change a little bit subject, and I'm going to talk to you about another kind of application. Again, these are examples, much more out there, but another application that shows you what people could do with deep learning. And one thing that we could do is to look for new physics. So I would like to explain a little bit why one would like to do that. So in normal configurations, when you say I'm doing science, what are you doing? You are following the scientific method in starting from data observations, formulating an hypothesis of what's going on, and then running further tests to verify it or falsify it. In high energy physics, the first stage, which is take data and look at them, it's somehow replaced by the fact that we start from the Lagrangian of the standard model. We don't look at data anymore as a first stage. We start from the Lagrangian of the standard model or some extensions of it. So we start already from the hypothesis, if you want, and then we go and try to falsify it or not. We completely missed this first stage, and we decided to do so as a community because we didn't want to bias ourselves and so on, but particularly because we have a very, very solid hypothesis to verify, which came with 30 or more years of tests to do. The problem now is that we're basically running at the end of this list of tests to run, and it's both in discovery, if you want, was maybe the last item to check in this list. So now what we do next, of course, we can keep repeating this problem and starting from some Lagrangian that the theories will give you. But one thing is to start from a Lagrangian standard model that has a solid basis of experimental support. One thing is to start from an extension of it, which could be substantiated by arguments, but there are many arguments up there, there are many Lagrangians up there, you don't know what's the right one. And somehow we decide to take that path as opposed to looking at the data and listening to them. So the idea is that this is not true in general in other fields, like astrophysicists look at data and follow this procedure. In particular, there is one thing that they do is that they look at outliers of their data in order to go there and look for weird objects, which might be manifest of new kind of physics phenomena that they didn't think about before. And we have lost a little bit in our way of doing things, this capability. Why? Because we have so many data that we cannot just do it. And this is where, again, deep learning comes at rescue, because we can use what is called unsupervised learning. Unsupervised learning is different than the one I showed before because it doesn't have labels. So you start from some training data and you try to answer some question, and which kind of question you are trying to answer is implicitly built in the kind of loss function you're trying to minimize. Typical example of unsupervised learning would be a clustering problem like jet clustering, like clustering detector hits into tracks, and so on and so forth. Now, there is one kind of unsupervised algorithm, which is called an autoencoder, which is effectively, it's a lossy compressor. So you start from some data X that lives in some n-dimensional space, and you want to have a representation of that very same input. So you are going from Rn to Rn, but in the going through a latent space which has a smaller dimensionality. So in other words, you're trying to learn the identity function as f to the minus 1 of f of x, where the first f of x, is compressing your n-dimensional input to some k-dimensional intermediate latent representation, which is of smaller dimensionality. And then the f minus 1 takes this reduced dimensionality and trying to expand it back to the original dimension. So this is a nonlinear equivalent of what you would do, for instance, with principal component analysis. And these algorithms typically were introduced to do things like data compression. So there are examples in deep learning that show that you can take, for instance, handwritten digit images and you can reconstruct them relatively well, of course, with some blurring, because in the compression and decompression, there is a loss of information because you have this bottleneck in the middle, which has a smaller dimensionality. Okay. One thing that the network does is that at once it learns how to compress and decompress different kinds of digits. And the different digits, of course, require different kinds of compression and decompression techniques. So your network at once is learning how to deal with different kinds of data. So if you look at them in the latent space, what the network is doing is that it's projecting different digits into different places of the latent space. So it could be seen also as a clustering algorithm. And now the interesting thing would be, what if you inject a kind of data that your algorithm never saw during the training? It could be that those new kind of data are clustered somewhere else in a different place. And so they could be highlighted as another kind of outlier cluster that doesn't belong to the clusters that are populated by the standard objects that you were training on. So in some sense, because the network is exposed to novelty, it will fail in doing this compression and decompression. And in average, you would expect you would expect the anomalies to populate the tail of the loss distribution. So if you take the function that you use to train this object, is the function that minimizes the input to the output distance. You will like, I didn't say that before. In this kind of compression and decompression, you will like x prime to be like x. So you will have some mathematical function that measures the distance between x and xy, x prime, which depends on the kind of data that you have. It could be mean square error, it could be something else. And then you're trying to minimize that because you want your network to learn to make x prime as close as possible to x. If now you inject something which is completely different kind of data, you would expect x prime to be very far from x, and so the distance would be larger, and so this could be a metric that you could use to identify outliers. Stupid example that I usually do is, to some extent, this is how a deep learning based translator works. You write in an English sentence, the sentence is converted into meaning, and then from meaning it's converted back into the same sentence in some other language. Now imagine that you have a very English to meaning to English, and it was only trained on English. It doesn't know anything else than English. If you inject a French or a German sentence, it would assume that it's English. So it will compress it according to the laws that you learned on how to compress an English sentence, and then would decompress it into some English sentence that would not look like the German sentence you injected. And so the input and output will be very far away. And so you have a mathematical way to isolate anomalies. In this case, these were like QCD jets as opposed to other kinds of jets. But the same applies to basically every kind of, this is how credit cards fraud detection works, for instance. Now, the idea would be, what if we're searching for new physics? How do we search for new physics? We start from 40 million events per second. We select 1,000 events which we think are interesting according to some preconception that we have on the new physics. This could be back in 2012, the Higgs boson with its multi-lepton final states, its diphoton final state, and so on. Supersymmetry with missing energy events, whatever. Extra dimensions with a lot of high PT objects, and so on and so forth. you could basically define these rule-based algorithms that tells you how to select these 1,000 interesting events out of these 40 million that you make. The problem is that here you are injecting a lot of human bias. You're injecting a lot of expectation of how new physics you think should look like. And not necessarily this expectation is correct. So why you keep doing this, and you have your reasons to do that, because there are mathematical reasoning and physics understanding, and physics intuition, why certain beyond the standard model models are relevant. You would like to have an algorithm that looks at the events that you throw away and finds the anomalous one, and select them and put them on a side for you, so that then you can go back and you can look at them. You can look at them one by one or whatever. And the class of repeating topologies that are unexpected, they are different than the standard model events. And maybe based on that, you will formulate the next hypothesis about some new kind of BSM model that you would like to test in 1.4. To do so, now the problem, what is the problem? The problem is that to do so, you need to be able to expose your algorithm to all the data produced by the LHC. And to do so, this means that you have to put your algorithm into the electronic of detector, because it's too, if you do this in a traditional computer, the first time an event gets into a traditional computer is the high-level trigger of CMS and Atlas, where you already went from 40 million events to 100,000 events based on some criterion that you impose. So your data are already biased. And if they're biased the wrong way, it's already too late. So the only way to do so is to put your algorithm in the front end, not in the front end, sorry, in the first level of trigger. And the problem that you have is that this first level of trigger actually is equipped with FPGAs. So you need to turn your neural network into an electronic circuit, into firmware. And so we came out with a library to do this. A library that takes a neural network and converts it for you into firmware, then you can integrate in your detector. Now, this is not just a translation problem, because the big problem that you deal with is that your FPGA, so the electronic device that we have on the card, can only host a limited amount of mathematical operations like multiplication that it can do. It cannot just take an infinitely large neural networks and host it and execute it in enough time. So you need somehow to compress the network and make it small enough such that it fits your electronic device. And we do so applying different compression techniques. Pruning, which means you identify which is the relevant part of, which are the relevant connections in your network, and you get rid of the others. Quantization, which is that you limit the numerical precision, the amount of bits that you use to do the numerical representation. And the reuse, which means that rather than doing all the calculation in one clock cycle, you use more than one clock cycle to take more time, but then you can recycle the components of the card in order to limit the amount of resources that you need. And then we apply this to a typical problem. How would you do it in practice? So you're living inside a system, the level 1 trigger, where you have very limited information about the detector because the reconstruction is very coarse. But as a matter of fact, you will have jets, you will have electrons or photons, you will have muons, you will have the missing energy. At some point in the level 1 processing, you have all these things at once, and you know the PT data and phi. So you know the energy that these particles carry and where they're going. You can use this information and try to feed an autoencoder this kind of data set. And you see that you can enhance, you can basically go and look for the very rare events, like 1 in a billion, 1 in a million, 10 in a million kind of probability. And you can enhance the signal over background by orders of magnitude with respect to the standard model when you got so tight. And this, I think, is something we would like to do. Now, can you take this and put it in the FPGA? The short answer is yes, but there are a little bit of some caveats in the sense that not all the architectures work equally well, and you have to be very, very careful in how you do this, because sometimes when you do this compression I was referring to, you make the network unstable, and by making the network unstable, you could actually lose a lot of performance. So by studying the different ways of doing the compression, what this implies in terms of anomaly detection, I think we're getting to the point that we have rules of thumbs on how one would like to do that. And before closing, I would like to, I'm getting some questions, I hope. I would like to show you something that we're working on now, which could bring this concept to some sort of next level. There is something which is called knowledge distillation, which we're looking at this very same right moment, which is a technique by which you don't, so what I discussed to you before is you define your network that you want to put in your trigger, and you try to make it as small as possible such that it fits the network. Instead, you could do something completely different. You start from a network which is as big as you want, okay? Knowing that this network will never manage to be put into an FPGA and runs within the right amount of time. On the other hand, you have another network, a smaller one. And you train this second network not to the problem that you want, but just to learn how to give you the output of the other network. What is the advantage? That in training an autoencoder, it means that your data are unlabeled. It's a very complicated problem. You don't know what's the right answer, what's the right function. And so what typically you do is that you use a huge neural network, knowing that this neural network could approximate a lot of functions, and in particular the right one. But once you have trained your network, most of your network is not actually useful. And this is why we do this kind of pruning, the things that you see on the top right, which is to a posteriori remove the part of the network which is not relevant to make it smaller. But identifying which part of the network is not relevant, it's a problem that's come with, it has issues. It's not like you're perfect in doing so. Instead, what you can do is that you factorize the problem. So one network learns the unsupervised problem and becomes a function that connects your input to whatever output this function is. At that point, you can use the output of the first network as the label for a supervised training of the second network, which we call the student. And this problem now is much easier. And so you might do it with a much smaller network that then you can prune, you can quantize, you can do all the things that I told you before. And now, what is the final dream? The final dream is that in the landscape of the problems that we typically handle in a level 1 trigger at CMS or Atlas, you might find an architecture which is small enough to fit your FPGA and large enough to be capable of learning the lesson from different teacher networks. So you could have a sort of a universal student that can actually teach different kinds of networks. That universal student might be, if you want, the OR of the different networks that you might need to do energy regression, jet identification, whatever you want to do at level 1. And
sorry to interrupt you, Maurice. You have 10 minutes left.
Now I'm basically done. So I'll leave the 10 minutes for questions, but I would like to finish a little bit in advance because I hope there will be questions. But my point is this universal teacher, student, you could print it. It could become a chip. And so you don't have FPGAs anymore. You go with your own chip. Chips are faster. ASICs are much faster than FPGAs. The problem of ASICs is that they are less flexible. This is why we like FPGA more. But now you are trading the flexibility of the FPGA with the flexibility of the algorithm that the chip encodes. And so this could be a new way, AI-driven, deep learning-driven, to actually go and implement triggers in general in the future. You could basically try, since you're leveraging the fact that the network is a universal approximator of anything, another network, in the case of knowledge distillation, or some other algorithm that you have. And then you can just print a network which is big enough to handle the typical problems that you have and live with it for 10 years. And this might actually open up the room for new generation of AI-based chips for energy physics. So my conclusion focuses on the fact that, so it's a little bit deviates from the Higgs itself, but it tries to put things in perspective. The LHC is a great discovery machine when you know what you search for. And the Higgs discovery is the ultimate demonstration that this is the case. On the other hand, the message that I try to convey is that we are confronted with a lot of technical and technological limitations with the LHC that are mainly due to the fact that the LHC comes with a gigantic big data problem, which means that we have to do things very quickly. We have to do things only on a limited amount of data. We have to get rid of data. We have to compress the information. And so at the end of the day, we have a very partial view of the LHC deliverable when we do offline analysis. And when we don't know what we're searching for, this is a limitation. So thinking to go beyond the Higgs discovery to the next big discovery, so far we assumed that the same methodology used for the Higgs discovery would have worked, but this is not necessarily the case. Now, since the standard model was established, this worked because we had in front of us a well-established path of discovery. We had the W's and the Z, then the top, we had speed violation, we had all the, and eventually we had the Higgs. And this is all great. I'm not criticizing it. This is just a fantastic, it was a fantastic journey, but my problem is that the journey is not anymore done on a very secure path designed by the standard model in front of us. Now we are a little bit more left into a situation of not being so sure about the path to take. And so this is where going back and looking at data, rediscovering the capability of looking at data beyond the paradigm that we impose ourselves, a blind analysis, could actually be a good way to make light in front of our paths. And so observational particle physics, the same way we do observational astronomy, could actually be the thing to go for. And I think that deep learning could be crucial for that, just because in any case, there are so many data that it's just not possible to look at them, even if you want to. So far, we didn't even want to, but if we want to, we have to deal with the fact that we cannot. So to me, the ultimate goal is really to use deep learning towards this line. And something we would like to do for N3, for instance, would be to create an anomalous events data set, something of the very rare events that she produced and we never looked at, and try to see from there if the community scrutinizing this data could get new ideas for random search. That's it.
Okay, thank you, Maurizio, for this very nice talk. And I can already see many hands raised here. Okay, so let's go with Ram.
Maurizio, can you hear me?
Yeah.
Yeah, so my question is about this definition of anomaly that you mentioned, anomaly detection. So because you are mentioning that whatever is different from standard model will be treated as an anomaly, so kind of like you are introducing a bias itself. Basically, just instead of standard model, it is not standard model is what basically you are looking at now.
Yeah.
So the claim of anomaly detected flowchart that you showed is that like it basically intrinsically depends on the standard model, because basically now you are looking at deviations from the standard model instead of some exotic theory on top of standard model.
Yeah.
So my first question is suppose some anomaly events have been detected by our machine learning algorithm and we are able to store this event, then how do we interpret it in terms of our usual understanding of what kind of interaction, what kind of symmetry, etc. can give rise to this kind of an event? Because by definition, we have thrown standard model away. Now we need some new theory or we need some new interaction to explain this anomalous event, but we don't have that now. But we have it stored this event inside our tape, on tape, and now we are looking at it. So how do we handle how do we handle anomalous events once we store them? That is my question.
There are different levels of ways you can handle them. And ultimately, this is intrinsically connected to which extent you trust your description of the standard model in the phase space you're looking at. If you could have some control sample or some Monte Carlo simulation and you trust enough to do so, you could even think of doing a data analysis on this data. There are techniques that actually let you look for new physics on these data sets, just knowing what the standard model looks like in terms of distribution of kinematic quantities, whatever you want, without having to specify what the signal looks like, which is what we normally do. It's basically goodness of fit test. But I would say that even if we don't want to be that ambitious, there is still a big lesson that could be learned from this data, just from the empirical observation that there could be events with probability of 10 to the -7, 10 to the -8, whatever, depends on where you put your threshold online. You could say, let's say that you store all the events which have a p-value of 1 billion or less, okay? So all these events are rare. Of course, there will be standard model events which are just happening because the statistical tail is populated and fine. But it could be that you start seeing things which are alike among themselves. Really lets you identify these particles. Imagine like the kind of algorithms that Spotify or Netflix or big companies that handle like these huge libraries of objects, songs, movies, or whatever, that are very different, but they could be alike from the point of view of people feeling, people taste, which is not even something you can quantify mathematically. So in this sense, their task is much more difficult than ours. We have a mathematical description in the back. So this kind of clustering algorithms could tell you that there is a concentration of events in your data set which have certain characteristics. I don't know. You have a lot of very soft photons and a very high energetic muon. I'm just making it up. This is the observation. This is where you would stop the exercise. You would just communicate this as a finding. I found a lot of events which have these and these and these characteristics. And then people will have to get creative and try to understand what this could be. And then people might publish, oh, I have this new model that could actually explain that anomaly. And then you will go in the next run and look for these things in a traditional technique. So one message I want to convey is that, to me, in the less ambitious manifestation, an anomaly detection technique is not gonna give you a number of sigmas, but it's gonna tell you where to go and look for new physics in the next round. Then you will be on your own with your own traditional techniques. And then out of those, you will get on the next round a number of sigmas and potentially score. I hope that I answered.
Yeah, thanks a lot.
Okay, let's go to Camelia. Please go ahead and ask your question.
Hi, can you hear me?
Yeah.
Yeah, thanks for the very nice talk. I was asking that how is this anomaly score calculated?
It's there is not a single anomaly score, and this is actually something that has to do with how you want to define this. There are people are proposing different things. Even out of a single algorithm like this one, that there is also the complexity that you could have even more algorithms in the. There are different kinds of algorithms of this kind. This is just the simplest example. But effectively, you are using a figure of merit to define the distance between your x and your x prime when you train. And you could use the very same quantity as the anomaly. So somehow it's not as a figure of merit. It's basically a metric of distance that you will learn during the training process. This is in the unsupervised flavor of this technique. So let's say that your inputs are the PT times phi of the particles, the way I told you here. Okay, you have the PT times phi of these particles in input, and you have the same thing in output. Opportunely normalized and so on. The loss could be the mean square error, which means sum across the particle of PT input minus PT output square plus phi input minus phi output square plus eta input minus eta output square. That's a stupid way of doing that, but it's a very effective one. This is what in the figures on the right is labeled IOVA, input to output loss. But there are other techniques which actually deal with the representation of these inputs in the latent space. So you could basically see, it's a little bit more technical, but there are autoencoders where in the training you try to represent your data as distributed according to some kind of n-dimensional Gaussian in the latent space. And so you could measure the distance of, so you take some event in space, you could use the distance of this point where you land from the center of this Gaussian in units of sigma. So it's a pool. And you could use that pool as an anomaly detection technique, figure of merit. So this is a little bit where the work is still ongoing in trying to understand what's the best choice. The point is that in this kind of game, what's best is not easy to define. And it might be easier to just do more than one thing at once.
Yeah. Okay, yeah, thanks.
Okay, Arnab Purohit, please go ahead.
Yes, first of all, can you hear me? Sorry.
Yeah.
Okay. So first of all, thank you for the nice presentation of, you discussed multiple things in this in the one single presentation. So my question, I have two questions. Can you move to slide 5 first?
Yeah.
Yeah, I'm really very happy to see these plots because it was in my PhD thesis. So I remember, I mean, as I worked on the photon identification in the Higgs-2 gamma and gamma. So basically, most of the machine learning algorithms that we use today are supervised, and they depend highly on the simulation, the truth. Mm-hmm. And what we see in several cases that the simulation does not represent the data very well, I mean, the real data. And that's why we get some discrepancies. As you can see, I mean, in this plot, the data which is in black and the blue bars are the Monte Carlo. I mean, actually, this is also scaled by, the Monte Carlo is scaled by some amount to match with the data. Which is also which the scale is also unknown. I mean, we didn't know what should be the scale, but we just tried. Yeah. So my point is that there are discrepancies between the truth, the simulation, and the data, and because of that, sometimes we also apply some uncertainty due to this discrepancy between the data and Monte Carlo, and which is sometimes is one of the major systematic uncertainties in our final results. So what do you think can be done to improve this in order to match the output of a network or ability both in data and Monte Carlo? That's one of my questions.
There are many ways to do this. There are techniques for when you train a machine learning algorithms. There are several techniques to do what is called a domain adaptation. So to translate what you learn on some kind of data simulation to another kind of data, the real data. Mm-hmm. This is done. There are two ways these are typically done that I know that were tried in energy physics, but this is an active field of research, so people come out always with new ideas. And none of these was done at this time, but we could have done some of them. I'm not sure how well these techniques apply to BDT. Certainly, they do very different. One is the adversarial training I was referring to before, to control the systematic uncertainty. So basically, what you do is that you could train your classifier, your ID, and you could penalize the training when so basically you could add a second network which is trying to regress the thing that you. I'm not sure. It's very difficult to explain it without a slide. I have a slide somewhere, but I'm not gonna go and look for it. And some other talk I have. So basically what you do is that you train two networks. One network is trying to accomplish your task, and the other network is penalizing the loss of the first network.
I understand, yes.
When it exploits features which are not in the actual data.
Kind of adversarial. I mean,
adversarial.
Yes.
The other thing is what is called a gradient inversion, where you basically it's a very technical thing. This was done in the jet in the long-lived jet identification of CMS, where you invert the sign of the gradient in the last in the last layer of this classifier, and then when you go and evaluate with data, you would get a big jump in the loss. So when basically you are exploiting a feature in your Monte Carlo which is not in the data.
Yeah,
there are ways of doing this.
Okay.
And I think that in general the flexibility of deep learning allows you, on one hand, there are two problems in the gradient that you refer to. One is how you minimize the dependence of your training on this data to Monte Carlo distance, which is the domain adaptation. The other one is how you associate an uncertainty to it, which again has to do more with variational inference. But both cases, I think, both answers can be found in literature. It's just a matter for us to exercise with these techniques and adopt them.
Okay, thank you. And the second question is slightly related to this, but it is like as you know, I mean, like the model works well in prototyping environments, but fails to generalize in the production stage. I mean, if you go to your slide 27, where you saw this the tracks being reconstructed using GNNs. No, now my question is how I mean, suppose how we shall deal with some unprecedented events, like suppose some part of the detector is not working, there's a hole in the tracker, let's say, or a module is very noisy and due to some reason, and it was not understood at the time of training the GNN. How I mean, and these things are being implemented at the trigger level, which means that if we lose some data, we may not be able to get it back. So how do you think it will affect?
I mean, this is already happening now with the standard algorithms. Your standard algorithms have the very same problem, is that your detector conditions are changing and not necessarily your training is made robust. How do you make sure your algorithm is robust? How do you make sure that your algorithm is robust? Typically what you do is that you try to fake data degradation and you try to see the effects of that. And you could basically do the same here. You could apply a training time degradation to your data and go with it. But it's also true that I mean, for instance, most of the particle flow in CMS were tuned looking at even displays of failures. So one writes a code, looks at the failures, oh, look, this event, and then comes out with rules in order to prevent that kind of failures. And here you could do the same thing. I don't think that there is a big conceptual difference between the two things. First, because you could embed the algorithm inside a rule-based algorithm. Second, because with GraphNets, you could embed the physics rules inside but these are all active area of research. I'm not saying that we have the answer already, but people are aware of these problems and looking into that. You could embed the physics inside the structure of your network itself. And finally, because at the end of the day, by defining an unbiased data set, you can fight the possibility of biases. So eventually, data augmentation techniques, where you introduce cracks in your detector and so on and so forth, and you're trying to make your algorithm stable against that, is, I think, one of the possible ways of implementing it.
Okay, yeah, okay, thank you.
Okay, we are actually running a little late, so we can take one last quick question. And Arnab Laha, please go ahead.
Hello, can you hear me?
Yes.
Yes, thank you for this very nice overview of machine learning in HEP. I have one question regarding the clustering aspect. So there are different other techniques such as TSNE or UMAP, which are also developed to preserve the multidimensional connection in a lower embedded space or latent space. Is there any effort to explore on that area too, like in the clustering studies, like the usage of UMAP or TSNE in HEP data, or there is some general advantage of using autoencoder based clustering over?
No, what I said about the clustering, autoencoders were an example, but people are looking into many things. And people looked into self-organizing maps, there are a lot of, the ultimate clustering algorithm doesn't exist, right? So people are trying different things. Of course, you could even do some kind of principal component analysis to replace an autoencoder to some extent, but the problem is that you are dealing only with linear manipulations of your data in that case. So at the end of the day, again, this is an active area of research. People are looking into things. The autoencoders, to me, are attractive from the point of view of the anomaly detection because they can be executed in relatively small amount of time. So they are trigger compliant kind of anomaly detection. But people, for offline analysis, people are looking at a lot of stuff, both for clustering itself, for anomaly detection and for other stuff. Unsupervised techniques, I didn't even mention, unsupervised techniques in general, not just specifically clustering, are also used in the context of molecular detector simulation, and people there are looking at other stuff like GANs and so on and so forth. So there is nothing exclusive about the autoencoders. I just discussed that because it's personally what I'm working on, and I'm working on that specifically because of the computational advantages thinking at an online environment, not because they are superior from a performance point of view.